Right. Is this where?
Yeah.
So yeah, thank you very much, and it's a great pleasure, a real pleasure to be here and have this opportunity to speak. So the plan is the following. I'm going to talk about this topic. It's not, sounds like fun, but you will see it's not fun. It's hard science. And then also, I thought it's a good opportunity to talk about some, maybe real life issues, but we'll see how it goes. Maybe before we start, can I ask, how many people here are students, and what kind of students? So are you undergrads or masters? So how many undergrads? Good. All right. And the rest is
there is no so.
Masters. Your master.
Some postgraduate there.
Right. Okay, good. So let's give it a try. Right. So the subject is very old. It's been around for maybe 400 years or something like that, and it's a question that challenged great people, Kepler, Leonardo, many others, and so it was noticed by, I don't know who, but first clearly described in Leonardo notes that if you take a typical plant like an oak or a birch or something like that, then the leaves on that plant are arranged in spiral, and if you count carefully how many turns you have per each step of the spiral, the number is close to the golden mean, to this square root 5 minus 1 over 2 or something like that, or more precisely, they noticed that leaf number 5 always comes almost on the top of leaf number 0, the one you started counting from, right? And then if you have a longer branch, then leaf number 8 will come a little closer, and the leaf number 13 will come still closer to be really on top. And so then, people interested in plant morphology explored this and found that it's more ubiquitous than just trees. And if you take any plant where you see spirals and count how many spirals you get, so this is a pine cone, and it shows how you count. So there are scales on the pine cone, and they are arranged so that you can draw spirals through them. Spirals in botany, they have a special name in Latin called peristices or whatever. And so if you count the number of spirals, you always get a Fibonacci number. Fibonacci numbers, just to remind, are a sequence that starts with 1 and 2, and then adding 2 previous numbers to get the next number. 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 13, etc. And so you can count spirals and find that the number of right-hand spirals is one Fibonacci number of left-hand spirals is another Fibonacci number, and even worse, they're almost consecutive in the sequence, so you can get pine cone of the type 813, or if it's a big one, it will be 1321 or 2134. And with sunflowers, if you take a giant sunflower, you can go as far as that. I even had once such a sunflower in my hands. And same applies to anything that has spirals. You can try yourself, and so that's the idea. Take a pineapple and draw spirals with scales, and then count how many of them you get. You always get a pair of Fibonacci numbers consecutive in the sequence. So that's the Fibonacci phyllotaxis, and that's the observation that was around for some time. Well, of course, the question that we're interested in as physicists is why plants are doing it. But I mean, before physicists came, to be interested, lots of people, had fun with it, classifying it, organizing it, etc. There's a long history that I'm not going to maybe discuss in detail. But let me first ask: do you see what this is? What are the spirals? How to count?
Can you describe
Yeah.
How to count? Just count,
Speak up.
for example. Can you describe in details how do we count? How do we count the intersections or what to get this series?
Yeah, so you can maybe start with this one. So this will be number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then that's the one we started with. So there are 13 red ones, and if you count green ones, and someone counted already, there will be 8 green ones.
And the green ones, it's there are also 13 green ones lines.
No. So there are 8. Yes, 13 red ones. We just counted 1, 2, 3, 4, 5, 13. And if you count green ones, there will be the number supposed to be 8. I haven't checked, but that's what this says. Right? So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So if you like, I have some collection here of fine combs that so I haven't counted, but I drew a spiral. On each of them I drew a spiral so that it's easier to start counting, and then you can yeah, no, they're supposed to work. I mean, all the same. So anyways, sorry for the interruption. So that's the idea, and there's a whole history of the subject, like I said, and so that's the quote that I already said about number 5, being about number 0, as he says, 6 is about the first one, same thing, and then lots of people studied it. Kepler, Alan Turing, and other people, and so the short story is that people for a long time were puzzled about the origin of it and didn't have a clear big picture. Various people proposed different explanations. I mean, obviously biologists were concerned with Fibonacci numbers being somehow beneficial for survival. So maybe Fibonacci number 13 is better than number 12 because it provides some better exposure for sunlight or better air circulation among leaves and plants. And so you can find theories like that in the literature. And it starts even with Leonardo, who himself said something like this, and he was way before Darwin. But then after Darwin and after genes came around, people started saying that maybe Fibonacci numbers are so good that they are programmed in genes, and the plants know that they have to grow in a Fibonacci way, and if it makes a mistake, if it, instead of 144 spirals it grows 145 spirals, then it will lose the battle for survival. But that, I mean, that from physics point of view, that's really, sounds like a bit of nonsense, because if you try to draw a sunflower with m right-hand spirals and left-hand spirals, you can very easily do that for any m and n, and the sunflower will be by eye indistinguishable from what you see here. So Fibonacci sunflower in its appearance doesn't differ from a non-Fibonacci sunflower. So it's not the geometry of painting, not the exposure to light. It's not, it's not anything that would be obvious to the eye. Something else. And yeah, so there is a question why, and some biologists realize that it's a problem that is outstanding, and I like this quote from this paper that says that to explain Fibonacci series is almost as important as to explain Balmer series in orbit, and they, the same way as they open the Levitov field around them. A Balmer series in spectroscopy, rather than Fibonacci numbers, we do the same thing for mathematical biology. I mean, may or may not go too far, but it's a good quote. Yeah, so the great hope of biomathematicians is that one day we'll know, right? Okay, so the day has come. Right. So now before we get to question why, let me also talk about exceptions. I mean, sometimes if you count, you find a pine cone which is not Fibonacci, but then if it's a non-Fibonacci pine cone, it's always from a different sequence. It's from a Lucas sequence that is obtained in the same way as Fibonacci by adding two preceding numbers to get the next number, but it starts from 1 and 3 rather than 1 and 2, and so in fact, I mean, I myself was first acquainted with this whole subject from the book by Hermann Weil, Symmetry, a long time ago when I was at school, and so in that same book, not only it's explained, but also Weil gives statistics on cones of pine trees, that is, there are so many pine trees in Norway, and people took trouble and counted and found that 95% were Fibonacci and 4% were Lucas, and others were some curved pine cones where we cannot really count spirals. So there are these interesting exceptions that also fall sort of in the Fibonacci framework called Lucas numbers. So that's point number one. Point number two is that if you pick a cone not from natural world, but let's say take a cuckoo clock, and there are these nice cones, and if you pick one at the clock shop and count, then the man-made cones, they are never Fibonacci. So they're always wrong. They're not Fibonacci in the number of spirals. Even though this looks very realistic, the clockmakers don't know that it has to be Fibonacci, so they're not Fibonacci. So it's much easier to find an exception like that than if you count real pine cones. Okay. So now let's see. Are there any questions so far? Yeah.
Is the Lucas number a generalized sequence, saying they can start from any numbers or only from 1 to 3?
Well, it's this sequence, and that's the name that it has. Lucas somehow has his name on that sequence. I'm not sure.
And is there a generalized sequence?
Well, yeah. I mean, you can start with any two numbers and then add them to get the next number, and then add them to get the next number. I don't think they have special names. They're just called generalized Fibonacci. I don't know what Lucas is famous for. Fibonacci is famous because he used these numbers for rapid multiplication or something like that, right? But Lucas, I never found out. But somehow, I mean, that's what Weil calls it. Weil is enough of authority to take this name. All right, so let's first, before we get to the question why, let's do a bit of geometry and do a mathematical model, work on mathematical models of these cones. Clearly, locally it looks like a lattice, and but it's a lattice on some curved surface, and the simplest way to model it is to first, approximate the surface by a cylinder, and say that it's a lattice which is wrapped on a cylinder. And if you unwrap it like this and then draw the lattice, and then you can obtain, you know, the mathematical model that people use in this subject. Lattices wrapped in a cylinder, and so the question in this form, the question can be formulated by saying, okay, so we have these, you know, plants, etc., and each of them can be abstracted to a lattice on a cylinder, and for some mysterious reason, all the lattices on the cylinder that we get from plants, they have Fibonacci numbers of you know, rows going like that, and rows going like this, and the question is why, right? So let's study lattices on the cylinder. This was, by the way, first introduced by Brevet, not the crystallographer, not the one who invented Brevet classes, but his brother. Clearly they talked, because this looks a lot like crystallography. Right. So the geometry of lattices on the cylinder, it turns out to be quite interesting. If you start with a lattice wrapped on a cylinder, unwrap it, and then parameterize it. The convenient way to parameterize it is to ask if you have these points ordered according to their height, then there are two parameters that you can introduce. One is the height of the first one above the lower one, and then, you know, the same will be the height of number 2 above number 1, and 3 above height 3 above number 2, etc. So there is a constant step by which they progress vertically. And then there is also an angle step. When you go from 0 to 1, you have to move by some angle. And you can think about it and see that these are the two numbers. All you need to know about lattice on the cylinder are these two numbers, and that defines it. Well, up to an overall scale change. We'll get back to that later. But up to an overall scale change, it's just these two numbers that characterize lattice on the cylinder. So I can parameterize all lattices on the cylinder by two numbers, and they can be, you know, combined into a vector if I so desire, and then it will be, you know, my phase space will be a point on the plane with Cartesian coordinates r and z or something like that, right? And so that's the phase space I will be working in. And then for each lattice, I can draw spirals, or draw lines that are unwrapped from spirals. And the way this can be done is that I will take a point here and then look at its nearest neighbors, which are these ones, and then draw lines through nearest neighbors, and then they will define rows, and then these rows, when you wrap it on a cylinder, become spirals, and you can count how many rows go this way and how many rows go that way, and that's the number of spirals. So now we have a clearly defined mathematical construction. We can parameterize lattices, all the lattices, by a pair of numbers, and then for each lattice a pair of real numbers, and then for a pair of real numbers parameterizing the lattice, I can count how many right-hand and left-hand rows or spirals I get, and get all possible types of lattices that I can construct. So if you actually do it, then what you find is that in this two-dimensional phase space, which is the height and the angle, and so here it's called x and y for uniformity, and also rescaled so that all lattices have constant density, so that we get rid of arbitrary rescaling factor. So then x, which is angle, and y, which is height, parameterize all the lattices, and then if you work on your geometry to find out where are lattices with different numbers of spirals, then you find this interesting arrangement, you find that there are regions in each of which the number of right-hand and left-hand spirals is constant, and these regions look in this funny way. They are bounded by arcs of circles standing on this line as a diameter, and so it's pictured. One of those is pictured here. Take circles with with corners of simple fractions, and then draw circles through them, and you get these domains that are domains of constant number of spirals. And so if you, it's not hard to do. It's a bit long, so maybe I don't want to do it in detail. Just trust me that that's what happens. But what's interesting is that you get, as we expected, you get regions for any pairs of spirals. So you get these domains called parastiki domains, because spirals are called parastikis in botany. And you get a domain for any pair of right-hand and left-hand spirals. So all mutually prime M and N are theoretically possible, and you can find a region here for 8 and 13, but also you can find a region for 7 and 9. There's a region for any pair of N, right? And so that's the set reality. So we did all this work. We don't yet see how Fibonacci numbers are special, but let's continue. So one can go a bit further by introducing geometric constraints. And now let's say we consider not all lattices which are theoretically possible, but only those which are obtained by close packing of disks. So I will take equal hard disks and then pack them into a lattice, and then ask where are, if I draw the corresponding points on my parameter space, which is height and angle, what do I get? It turns out that if you use this phase space that we defined, height and angle, then the closed packed disks, lattices formed out of closed packed disks, they form this interesting tree-like structure. The branching points occur at the points that correspond to densely to perfect triangular lattices. And so, you can understand it in the following way. If you have a perfect triangular lattice, then you can deform it in 3 possible ways by making one of the sides of the triangle longer, and because there are 3 sides, you can go in 3 different directions, and that's how your perfect triangular lattice can become skewed, can become, or dilated, can become dilated in 3 different ways, and so that's roughly what happens near these triple points. Okay, and then the arcs connecting them, you can think about it as a closely packed, as a lattice of hard disks, which is slowly evolving from one triangular type to another triangle. It's a bit complicated to picture it in your head, but actually I don't want to get into that story. That there are papers by geometers written on it. It's very beautiful, but the essence is that you get this branching construction. You get a tree, and again, for any pair of numbers, you can find a branch on the tree where this pair of numbers is realized as right-hand and left-hand spirals, and so you don't distinguish in this way Fibonacci from non-Fibonacci. You see that there are Fibonacci, but also non-Fibonacci, and so this one is Lucas, and this one is Fibonacci, and there is room for everything, right? So you don't. So what we learned so far is well, somewhat useful. We learned that we know how to parameterize cylindrical lattices. We introduced phase space, and we mapped out the regions with constant numbers of spirals. Also, having said that, but if you're familiar a bit with hyperbolic hyperbolic geometry, Lobachevsky, etc. Right? Then if you look at this picture, it will strike you immediately that this is actually all hyperbolic, and maybe the right way to do it, to think about, is measure distance using Lobachevsky rules rather than Euclidean rules, and we can get to that later, right? But that clearly follows just from the appearance of these objects, right? But I mean, the bad news is that it doesn't explain why Fibonacci numbers are special. So then we get the physics part. I mean, I don't know, maybe stop and take some questions. Is there anything here?
Yes,
everyone
like
completely lost it? Yeah.
Yes. Can you explain what is triangle lattice? Because we don't usually hear about triangle lattices. We usually hear about usual rectangular or rhombic lattices.
Right. So this is, I mean, triangle is a special case of orthorhombic, I think. So if you imagine, so this is a square lattice, right?
Yes.
And then if you deform it like this, and at this point it becomes two equilateral triangles back together. And now if you start with a square lattice and deform it this way, then you get another triangle lattice. So you can from a square lattice you can deform it in two different directions and get a triangle lattice, and that's what's going on here. So if you ask me where are the square lattices, they actually live at the midpoints of these arcs. And if you go from a midpoint one way, you do this, and if you go the other way, then you do that, right? So and in each way you arrive at the triangular packing of hard disks, and then once you're at the triangular packing of hard disks, then you are, I mean, you can go three possible directions, right? Preserving dense packing, you can go in three possible directions, because each in the dense packing, each at the triangle point, each disk touches 6 neighbors, and then you can undo a pair, one of the pairs of these 6 neighbors. Then it will be touching 4 neighbors, and then it will be your orthorhombic lattice. And you can choose pair 3 different ways, and so that's why you get this branching. And it's not easy to picture, but actually we don't need to get into all these details. The important thing is that it's been done, and it was done actually by some this construction was done by some biologists who were hoping to explain Fibonacci numbers in this way, and they worked out this construction, and then Fibonacci numbers turned out not important in this construction. But it's useful to show it because it will show up later in something else. Any other questions? Yeah.
Are these lines continuous or dot?
Right. So this is something. Right. This is something maybe let's come back to it later. Maybe since you asked, good. So let's say it now. So the biologist who introduced it, he also noticed that if you try to actually create the structure not simply by drawing circles which are densely packed, but think of some contact pressure between them, then if you calculate contact pressure, then in part of this diagram, contact pressure will not be positive. So it's a bit complicated. It will become much clearer, 3 slides later. But he noticed that if you think about this densely packed lattice obtained from contact pressure, then contact pressure doesn't make sense in part of this diagram. So that's the total line. But we'll get back to that. Right. So what I want to present now is a physical model which is purely mechanical, and the idea is basically to build on what we just learned and try to stabilize the lattice by some forces by which the units are repelling each other. So we'll introduce some energy function, take some potential forces, potential that defines forces by which units of the lattice are interacting, and physically it will describe contact pressure between the units on the plant during growth. And what we are going, so we'll take interaction which is some repulsive interaction, and at this point we don't care which one, and one can show that most of what we're going to say is not going to depend on the type of interaction as long as it's repulsive. The game that we're going to play is that we'll take a simple lattice, maybe corresponding to all units arranged in one row, and then start squeezing it along the cylinder axis, and then let it do whatever it wants to minimize energy at every stage at which we squeeze it. And physically, this will describe an isotropic growth. So imagine that before pine cone became rigid, it was some soft embryo. I'm not sure if embryo described is the right word for a cone, but it was soft on some unit. When each scale was just a few cells, it was a soft one, and then it was expanding because cells were dividing, and it would expand equally in all directions, but because it was inside a hollow or a cavity, it was subject to an isotropic constraint, so it was easier for it to expand sideways than along the axis. And so it was an isotropic growth, or if you forget about overall descaling factor, you can just say that let's take the lattice on the cylinder, squeeze it along the cylinder axis. And it turns out that that's a fairly simple problem that one can analyze and show that if you play this game, then you generate Fibonacci numbers, structures with Fibonacci numbers. So basically, what I'm talking about is a history of a lattice deformation induced by growth, or if you like, induced by stress. They take the lattice on the cylinder and start squeezing it, and track energy minimum. So this function, which is a function of x and y, will have some complicated dependence on x and y, but the fixed y, the squeezing parameter, I can look for minimum on x, and then I can track these minima, as y decreases, and draw trajectories, and trajectories turned out to be very interesting. So for example, this is the trajectory. I only drew it in half of the phase space because x on this side corresponds to chirality change to the opposite, right spiral becoming left spirals, left becoming right. So there's nothing new here. This will be a mirror image of what we see on this side. But on this side, what seems rather interesting. What we have, we first have the simplest layers where the units are arranged in an alternating order, and then it comes to the point where bifurcation occurs, and lattice acquires chirality. It becomes right-hand spiral, left-hand spiral. But then after that, this principal trajectory doesn't bifurcate anymore, and what it does instead, it goes through all the domains with Fibonacci numbers and nothing else. So all Fibonacci domains are on the principal trajectory that you obtain by squeezing the simplest structure, and all non-Fibonacci numbers are out. They don't appear on this principal branch. So that's interesting. Then if you also ask where are the Lucas numbers, you find that to get to the Lucas numbers, you need to make a mistake here. So if you squeeze it up to this point and then somehow jump, so you violate your condition that you're tracking the minimum, jump, let the system go over barrier or something like that, and then continue tracking the minimum by continuity. Now it will be a different minimum. So then this minimum that you obtain by making the first error and then no errors after, so that will be the trajectory that generates all Lucas numbers, and then if you make many mistakes, you generate some other numbers, but apparently real systems don't get there. So that's the result. So there is this deterministic process by which Fibonacci numbers are obtained by increasing stress applied to a lattice, and so it's simple enough, and also can be shown to be independent of the kind of potential. So you can vary potential, take different kinds, and you see that this behavior is very generic, and because generates naturally Fibonacci numbers in a deterministic way, also generates Lucas numbers under natural assumption that we're allowed to make one mistake only, then maybe convincing enough to say that maybe it's not really genes, maybe it's just a result. Fibonacci numbers are a result of a deterministic growth process in which system is stressed, and out of the stress, Fibonacci numbers come out naturally. Right now, you're going to ask me. Someone is going to ask me at this point. I'm sure. Are you actually minimizing energy for real, or are you doing something else? So I'm not minimizing energy for real. I'm not at every compression, every degree of compression. I'm not looking for the lowest energy state. If I would do that, then my trajectory would jump erratically between these different branches. Because if I compare energies of these lattices, I will find that some of these lattices have lower energy than other lattices, and which one is lower and which one is higher depends depends in some crazy way on the degree of compression. And so if I look for global energy minimum, then it will show some erratic behavior which is very different from this one. To get the right behavior, you don't want to minimize energy globally. All you want is to track a local minimum that appears first here, and then just follow it by continuity, and you are done. You don't care about minima which are far away that may be more energetically favorable, but they're too far to be reachable. So we see that basically. So that's the key observation. We see that by varying this parameter y that describes the compression degree and theoretic energy minima, we obtain deterministically all the Fibonacci numbers, and then other trajectories give generalized Fibonacci sequence Lucas. And so this behavior, you can see that the behavior is completely robust and doesn't depend on choice of potential, provided it's repulsive. So that's the conjecture, and then one can work and actually prove it, which is what some papers written a long time ago. But also maybe instead of getting into that, people actually did an experiment. What we described was simple enough to realize the mechanical model, and people did just that. They built something that they called magnetic calculus, and that's where it was published. And so what they've done is that they've taken an axis and put some bearings in it, and each bearing had a bar magnet sticking out, and the bar magnets were very strong, neodymium magnets, so they repel each other. They all oriented with the north pole, let's say, out and the south pole in. So they all repel each other, and because of that, they want to. The bearings want to rotate, so the magnets are as far from each other as possible. And so if you start with a simple structure like that and then anneal it, they say, the system can be annealed into low energy state by mechanical agitation. So if you start with a simple structure and anneal it, or just let the gravity do the work, then you get the spiral structure, and the spiral structure, there are several kinds of spiral structures they get, all corresponding to Fibonacci numbers of right-hand and left-hand spirals. And so that's the proof that the real system was doing just the same thing as simulation said, right? So at this point, we can stop. One can also try to prove all these statements mathematically, but that requires doing some math. Maybe I just state the key facts for fun. So what what you can do, and that simplifies your analysis a lot, what you can do is to make an observation that because these curved domains are so suggestive of hyperbolic geometry, you can ask whether there are hyperbolic translations, and hyperbolic translations are these fractional linear transformations where you have to take x and y and make a complex number out of them, like this, and then do a fractional linear transformation of a complex number. Then it turns out that you can construct a set of translations that will be symmetries of our energy. So the energy functional that we introduced somewhere here, it didn't seem to be symmetric. But in fact, it is symmetric if you interpret x plus iy as a complex number, and then you find that if you perform a Möbius transformation, fractional linear transformation with a, b, c, and d being a unimodular integers forming a matrix with union determinant, then that will be an invariance transformation for the energy. Energy will not change under this transformation, right? So as a result, the energy contours, if you plot energy contours on this plane, then you will see that they all look the same in each of these triangles, and that so you can use this fact. I mean, you first prove it, and you can use it in the same way as we use periodicity in studying crystals, because periodic function repeats itself throughout the space. All we need to do to analyze the behavior is to study it within one unit cell. And so the unit cell here is one triangle. And so if we understand what the system does in one triangle, we can extend it to the entire phase space. And so that's the idea of the proof. So now what you need to do is to think about these trajectories, and you can do another fractional linear transformation, map a half plane on the unit disk, etc. These are details in a sense. The main thing is that there is the symmetry of energy that you can use to simplify your analysis and think about what happens in one triangle. And then in one triangle, you find that the trajectories do this. There is a trajectory that enters the triangle from above and then exits it from below, and then another trajectory appears on the edge between this triangle and next triangle, and then enters the other triangle, and then everywhere it looks the same way, and it doesn't look identical because we shouldn't use translations to connect triangles with these hyperbolic transformations. But if we use hyperbolic transformations, then we'll see that the behavior is actually identical in all the triangles. And so from that you go smoothly to Fibonacci numbers, and then at this point you're done. Okay, so that's we have to do a bit of math here. I don't want to do in front of so many people, but the idea is you just use symmetry, use the fact that this energy has hidden symmetry, which is hyperbolic symmetry in these Möbius transformations in the hyperbolic plane. And so that, whether you like it or not, that is at the heart of the Fibonacci numbers. And if you don't like it, you can just say, let's do an experiment, make a mechanical model, and then stress it and see that mechanical forces only are sufficient to generate Fibonacci numbers. Okay, so the conclusion is that we don't have to rely on genes to get Fibonacci numbers. Simple mechanics does that for us. And let's see if there are any questions. Yeah, sorry.
Was there any experiments growing up some plant in space where there is no gravity?
Yeah, I don't know about, sure, people tried that. I don't think gravity is an issue. I think the issue here is to, if you want to do an experiment with real plant, the issue is to somehow look at what happens at the very tip of the plant where the new future leaves appear and before they solidify, right? And people actually done that. There is some literature, people try to dissect the very top of the plant and look how these soft objects later will become leaves, etc., or how they organize themselves, but somehow it's a little messy and not much can be said. But yeah, in principle, that's where things happen.
And what about the sunflower? Basically, we here was talking about vertical pressure when something is growing up, and in sunflower it's not in vertical direction but in horizontal
right
direction.
So in fact, yeah, I showed this experiment not because it's the first one, but because it's the one which is closest to my heart, so to speak. But in fact, at the time where when this paper was written, there was an experiment. I mean, not this paper, my paper. There was an experiment that was a mechanical model of a sunflower. And so what they've done, so this was done in Paris by some people who were studying ferrofluids. So what they've done is the following: they had a dish with oil in it, and a pipette that was releasing droplets of ferrofluid into a dish, and there was a magnetic field applied so that each ferrofluid droplet would become a dipole, magnetic dipole, and all these droplets, imagine droplets coming into the dish, and they all are repelling each other, and they come one by one at the center. And so they looked at the patterns as these droplets form when they are pushing on each other and flowing out. They form spirally patterns, and you can control number of spirals by increasing the rate at which droplets come out from the pipette. And you can see that if you increase that rate, you get more and more spirals. And I mean, they couldn't get to 144 or even 35, but I mean, they generated higher Fibonacci numbers than in this experiment. And also they checked that non-Fibonacci didn't appear.
So where do they apply pressure?
So like you said, it's at the center. I mean, it just applied because you release your objects in the center, like I mean, the reason you ask is that in the sunflower clearly there is a growth center at the center when new units, new seeds or whatever are generated.
So does jumping off any bifurcation point of main trend lead to Lucas points or to some other points?
Right. So if you wait and jump later, then if you don't jump here, but let's say you wait and jump here, then that will be another generalized Fibonacci sequence, which is not Lucas. Lucas is this one. So
what are energy barriers between these things? Are there any calculated energy barriers for these jumps?
Well, energy barrier will depend on this potential. I mean, you can see that energy barrier grows, the further you go, the bigger your object becomes, the higher the energy barrier, because up to here it's a fairly simple structure, and here jumping means there is a lot of rearrangement.
So it scales.
Going further,
it scales up with, it basically scales up with number of seats.
It scales with circumference, scales with how many units you get in the circumference. Yeah.
Why is this first jump is most probable?
Well, probably because the barrier is low. Yeah, so the barrier, I agree, it grows roughly with how many units you have in the circumference.
So how it scales up to real pine cones? Real pine cones have a non-cylindrical geometry, and basically there is more points and the veins of pine cone.
Yeah, no, I know. no. So the real pine cone is not a cylinder. It's also not sunflower. It's some complicated curved object, and nevertheless it does that. So maybe, yeah. I mean, there is no.
And
no,
also,
no one. I mean, no one tackled like seriously curved geometry, but because people did it on a cylinder, both theoretically and experimentally, and also people did it in a sunflower geometry, and pine cone is somewhere in between. Maybe it's also covered. And maybe there's something there to do.
the theoretical model has a cylinder which is not limited in either direction.
Yeah.
So if you take pine cone which is terminated, what this termination point does in this model? Can you model this termination point somehow?
No, I never thought about that. So the growth point of the pine cone is not where it's attached to the branch, but at the tip, right? So probably everything happens there, but while it's soft.
So is there some number which corresponds to normal bulk number, or other less or more seeds at the base? They're smaller, as we see, but can we see the continuation of the trend to termination of pine cone?
Yeah, no, I don't know. No, it's a complicated geometry that is hard to think about what this means. Yeah.
Thank you.
Curvature, termination. Yeah, that's it. Yeah.
A lot of time for questions. Please don't be shy.
No, I have some. I have another topic to discuss for some time. So, Nisha, when are you supposed to start?
At the starting time, we're going to take a short break.
Next lecture starts in 10 minutes.
So, can I take 10 minutes?
7.
Yes, sure. 8. Okay. Right. So, okay. So, yeah. So I wanted to talk about maybe spend 8 minutes, 7.5 minutes, talk about non-physics. So I've been discussing for some time with various friends from Eastern Europe, and in particular from Ukraine, how Ukraine will, how science in Ukraine, education in Ukraine will move into the future, and some ideas on that I thought might be interesting to bring up, because we have this opportunity that we're here, all of us are here. And just to explain the background, maybe let me say that my background is that I come from a university which is a research university, and a research university is a place where students not only study, have an opportunity to do research at the same time. They benefit from it in many different ways, and it's a model which is very successful in the West, and we see why is it successful, and so it's kind of interesting to have a discussion between East and West and compare different approaches. But because I only got 6.5 minutes, let me just quickly say what's on my what I have to say, and then maybe we can have discussions later. So at my place we have research which is going on at the same place where students study, and all labs are open to all students, regardless of what their specialty or major or whatever you call it. Here, either undergrads or master students. Actually, we don't have master students. We have students who study for 4 years. So starting from year 1 to year 4, all students are welcome to the labs, and they're allowed. Not only allowed, they're motivated to do research, and more on that later. And the toy research they do often, morphs into real research, and it's a really exciting experience, because this way education and research are integrated. And there are several ways this is that achieve this. And one way which I think is special for my place, MIT, not many other places have that, is this program called Europe, which is undergraduate research opportunity, which is when students during the term, during the semester, they spend some time in the labs working on the research, and that's very good for researchers, because students are full of creativity and energy, and it can be a spark that lights a fire. And from an undergraduate student, doing Europe is a very interesting thing, because it allows to gain real research experience in virtually no time, and it's a little bit like learning to swim or just jumping and then either doing it or not doing it. And also it brings a sense of accomplishment, and also you get, in some cases, some income. So both students and faculty appreciate this very much, and we think that this is one of the main main selling points, attraction points of MIT, because other places don't do that, or do it at scale. So there are many benefits that this has, and we see. So all of us spend some time with undergrads doing research, and then that helps them to start a career in research, in industry, in university. Later, go to grad school. We also have partnerships, networks with other universities that have this Europe system, and we have student exchange within that Europe program. And so there are, in particular, I was involved recently in such a thing with 2 places. There is a Europe program at Imperial College in London, and also something similar at ETH in Zurich. And so we have some exchanges of Europe students. I mean, they study during the semester at their place, but then for the summer they can go elsewhere. And also with ETH, because it's a European system, not an English system like us, it's 6 years, so they have master students, so there's a change of master students, which works pretty much like Europe. So there is that, and that is very successful, and it's interesting to discuss if there are ways to somehow expand this experience, extend this model, and maybe realize it elsewhere. So that's thing number 1 that helps to engage students in real research. And you can learn more if you go to the web and just type Europe MIT. Europe stands for the Graduate Research Opportunity, but if you just remember this acronym, that's enough, right? Then also there are various summer programs that I think is useful to bring up, because many people here are undergraduates, right? So there are summer programs. MIT does not run any summer program on its own. There are other entities that run these programs, but many of them happen on MIT campus, and in summer, even though we're not open formally to undergrads, you see lots of undergrads on campus. And for example, there are many of these programs. Again, if you go on the web, you find lots of them. The one that I've been involved in particular is called Research Science Institute. It's a summer program which brings together about 70. So on the website, it says high school students. In practice, I know that from Eastern Europe, they often get undergraduates. So I personally dealt with one undergrad from Poland, one from Belarus, one from Russia. Somehow there's no one from Ukraine, but it's very easy to apply, and what happens there is that participants attend college level classes and then also do some baby research that often morphs into some real research. And then when I tell this to my friends, in particular from Ukraine, they say, "Oh, this will cost a lot of money." Now, if you look at the website, it's actually written there that it's free for all. Maybe it's not so easy to get in, but it's free for those who are selected. MIT is not involved in this financially, but we provide assistance when we ask to mentor someone. And there are many other of these programs. Some of them require tuition, some not. But I mean, this one, which is very successful, I think you should know about it because from what I have seen, the bar. I mean, the Ukrainian students who I know personally, they all clear the bar for that program easily. So it's strange that no one showed up there. Right, then, so that's thing number 2. Thing number 3, yeah, 30 seconds. Thing number 3 that exists, which is also, I think, a good way to integrate in a Western type system, are various summer schools, which are international, and there is a set of traditional, well-organized summer schools that they all accept international students, and I think people should know about them. And undergraduates, I think, are welcome. So there is a very well-organized Volga summer school. It aims maybe at the master level, but strong undergraduates can also benefit from it. And then there are also these places, in Europe, in Dresden, and Vazush. There is also a program at Weizmann Institute. Maybe people from Weizmann Institute will say more about it. So that aims specifically for undergraduates. So it's a semester. Sorry, it's a few months in summer that you spend taking classes. Basically, it works the same way as this thing you talked about it here. You take some classes and then do some research, and it's fun. And you get in virtually no time you get a unique research experience and unique exposure to various ideas that you don't have at home. And it's very popular around the world. And I have friends who are now distinguished scientists, that they are Americans by background, who attended this, and I think much of what happened to them later was because at the early stage they attended some summer programs, right? Then there are also other summer schools, Windsor, ICT. Yes, there was a very good school run in Russia by Dynastia, but Dynastia was kicked out of Russia recently. Maybe they will move to Eastern Europe. That's the hope. And then because the people who were enthusiastic, they're all there, and there is some force that they could apply those guys. Right. So all of these schools, they have different deadlines. You can check on the web. Some of them accept people only for money. Some not. There are schools that open. Some accept international students free. And then also, okay, so I can continue the list. There are also various other summer programs. Maybe I should let Grisha, compete for it. But then there are also various summer programs for, again, nominally they are announced as programs for high school students, but I know for certain, because my kids attended some of them, that there are undergrads, in particular from other countries, in many of these programs. So, for example, I know for sure that this one, Canada US Math Camp, has lots of undergrads from Europe and from Asia. Same. I know about that much because I have kids there. And so that I think you can find this list on the web if you use Google, and if you don't know how, ask other people, ask me. So this is all very much worth looking for, and we'll be happy to continue in person. Grisha, sorry, before we 3 minutes of your time.
Wonderful talk.